Okay, so 2010 number 4, we have a region. It's bounded by y-axis, the line y equals 6, and the curve here is y equals 2 radical x. Okay. And so on part A here, we were asked to just find the area of this region, and so ultimately it's got a top, that's the horizontal line. It's got a bottom throughout the region, that's the 2 radical x. So if we write our integral from 0 to 9, 6 minus 2 radical x dx. And this is a non-calculator problem here in number 4. So therefore we'd have to do it with the fundamental theorem. So if we get our antiderivative here, 6x, and then x to the 1/2 is our x squared of x part. So it would be x to the 3/2 times 2/3, and we had a 2 out in front also, so that would make it 4. And if we evaluate that on 0 to 9, we could get 6 in here would be 54, and then a 9 in here would give us 9 to the 3/2. If we do the square root part first, it would be 3. Raise that to the 3rd power, would be 27. So 27 times 4 would be 108 over 3. 108 over 3 is 36. So we'll get 54 minus 36 for that part. And putting a 0 in gives us 0. So ultimately we get 18 as our area. And believe it or not, that's worth 3 points. So getting the right integrand, you had your 6 minus 2 radical x as your integrand, that's worth a point. Do you have the right antiderivative? Another point. And the right answer, another point. Questions on any part of number 4, part A? Alright, then part B, the question is write but do not evaluate an integral expression that gives the volume of the solid generated when r is rotated about the horizontal line y equals 7. So ultimately, again, same picture. If we have y equals 6 here, and we rotate that over the horizontal line y equals 7. We know that for our particular purposes, we could use shells or discs. In the AB case, AB topic is discs and washers. Shells is actually a BC topic. So depending on what class you had, you may not have even known about shells at the time. I know we did, but ideally they're looking for a washer setup here. You could set it up with shells and not get it wrong because, like I said, on the BC test, shells are okay. They're actually okay on the AB test, so if you know them, you can use them, but you don't have to know them because you can set this up without it. So bottom line here is with our shell setup, if we have a vertical slice, we're going 0 to 9 again, pi, and then we need outside radius squared minus inside radius squared dx. So that's what our setup will look like for our washers here. And in this case, the outside radius is going to be this distance right here. So we know that this distance right here is 2 radical x. True? So that means that the distance of the shell itself would be 6 minus 2 radical x, just like we used in the last part. But again, we want the distance from the outside of the shell, or outside of the washer, I should say, not the shell, outside of the washer to the revolving line. That distance would be 1 plus the 6 minus 2 radical x. So ultimately it would be 7 minus 2 radical x. And then the inside radius of the washer will just be that. And throughout that region, no matter where I draw that vertical slice, the distance there is simply 1. And it says write but do not evaluate, so we don't have to do anything with that. We just need to leave it as is and collect our points. So points here, 2 points for the integrand. When they do the point breakdown, I'm not 100% sure if you get, like if you got that right and that wrong, that you get 1 out of the 2. I'm thinking that you would get 1. And then also if you have 0 to 9 in the pi part of the equation, and the 0 to 9 part, you get another point for that, so 3 total. Okay, questions on that washer setup? Alright, and part C, we're using that r as a base for our solid. And it says for each y between 0 and 6, the cross section taken perpendicular to the y-axis. So ultimately we're looking at, this time, a horizontal slice, and a slice that's perpendicular to the y-axis. It says each slice is a rectangle whose height is 3 times the length of its base in this region R. And again, write but do not evaluate an integral here. So keep in mind that when we have this, this is our base and we have a solid coming out of the paper at us, and it's a rectangle, and again it's difficult to draw in 3 dimensions here on a 2-dimensional paper, but ultimately we have coming out at us a rectangle from this slice. So this is our one dimension, the other dimension is coming out of the paper at us, and we know that if we're going to do this in y, we're going from 0 to 6, we know that much. Okay? And the question is, can we write an expression for the area of that rectangle? Well, keep in mind that no matter what the circumstances are, we're going to write down the formula for the area of a rectangle in general and see if we can write that in whatever variable we have here. So in our case, we're going to try to write it in y. Well, that distance right there, what's that dimension right there? Well, that would just be the function solved for x, wouldn't it? So for our case, if we did the y over 2, we divided by 2 for our original function and then squared both sides, we'd have x alone. We'd get y squared over 4 equals x. Okay? So that distance right there, and again this represents anywhere that I draw the slice in the region. I chose to draw it there. You could have drawn it down here or up here or whatever. The bottom line is that distance is x, and that x is equal to y squared over 4. So that would be one dimension. Okay. And now what about the other dimension? The dimension that comes out of the paper at us is, they told us what? 3 times the length of that. So ultimately that dimension would be 3y squared over 4. And we would have now an expression that is the area of that rectangle that I have drawn. Okay. Simplifying, we'd have 3y to the 4th over 16. So that, again, would be the area of that one rectangle that I have drawn. And if we want to sum up all the rectangles that are made in that region, then we would integrate that from 0 to 6. And with that, we'd be done. So there is our expression. We don't need to evaluate it. We just need to write the expression that would give us the volume, and that's it. So 2 parts here, 2 points for getting the integrand right, and 1 point for ultimately having all the rest, I guess, the 0 to 6 and the dy. Okay. So ultimately, it's essentially just 1 point for having the limits right. Okay. Questions on C? Alright, well, let's take a look at number 5 then. And keep in mind this was, we've seen this problem before. This was a BC or an AB problem as well. AB for 2010. 2010 BC 5 though is not an AB problem because it starts out with Euler's method, which is a BC topic. So the information that we're given is that we have a differential equation, 1 minus y. We have an initial condition given, and it says for this particular solution, the f of x is less than 1 for all values of x, so keep that in mind. And then in part A here, it says to use Euler's method starting at x equals 1, and it says with 2 step sizes of equal size to approximate f equals 0, and show our work that leads to our answer. So ultimately, if we're going, we already know that f of 1 is 0, keep that in mind. Okay. They gave us that information. And we want to be able to get an approximation here for f of 0. And so with that, we ultimately will do our Euler's method. Remember, it's just like a linearization. We're going to start with the value given, which is 0. Okay? And then we're going to add to that the derivative at the point in question. And so our point in question is, let's say it would be 1/2, I guess. And this would give us f of 1/2, because they said two steps of equal size to get to 0. So that means we go to 1/2 and then we go to 0. So they said 2 steps of equal size. So we'll first want to estimate f of 1/2. Alright, so again we're at this value here of 0, and then we're going to add to that the derivative times the step size. So ultimately we need to know, first of all, and let me generalize that. Remember the linearization here is going to be put y sub 0 plus f prime of x dx. I don't know if that's the exact notation that your book uses or not, but that's ultimately what we're doing here. Because the new approximation is going to be where we were at the beginning, plus the derivative times the change in x. So that means that our derivative here is 1 minus y, and keeping in mind that that this derivative is going to be the derivative at this same point right here, so that means that our y sub 0 for us is 1 minus 0. Remember our initial y is 0, okay? And therefore our derivative is going to be 1 minus 0, which is 1. And then what's the change in x? We're going negative 1/2. So the change in that x here, keep in mind we're going from x equals 1 to x equals 1/2. So the change in x would be negative 1/2. And so that would be our approximation for the function at 1/2. And when we do that again, when we want f of 0, when we go another half, keep in mind we're at negative 1/2 already. So we go with our previous approximation. Okay. And then we want the derivative at that point. Okay. So the derivative at this point, remember this is a y value that we found. Okay, so the derivative at that point would be 1 minus negative 1/2. So ultimately my derivative would be 3/2. And I'm going to multiply that by the change in x, and the change in x is another negative 1/2 because we went from 1/2 to 0. Okay. And with that, we will have minus 3/4, which ultimately would be negative 5/4. Alright, so again, this is essentially the iterative process that we got to make sure we memorize here for Euler's method. Is that we have, if we understand that this is ultimately all we're doing here, then it's not a terribly difficult problem. We just, to get any new y value, we take the original y value, and we add to it the derivative at that point, at this previous point, times the change in x. So again, we could continue this if we wanted to. If we wanted to go to negative 1/2, just for argument's sake, we'd start with negative 5/4. So keep doing this process over and over again as many times as we need to, and ultimately we're going to add the derivative at the previous y, which is in this case negative 5/4. So if we subtracted negative 5/4 here, we'd have 9/4. 4/4 plus 5/4. And then again, the step size is still negative 1/2. And we'd get a new answer, and then we just keep that process going over and over again until we have as many approximations as we need. So again, the key issue is that when we use that method, that's really all it is a linearization. We're doing the y value that we were at plus the derivative of derivative of the x or y, because remember some differential equations are written in terms of x and y, so we might need both points to get an answer for the derivative part. Okay? We might just need an x, we might just need a y. Okay? But either way, it's the derivative at whatever point we were just at, okay, whatever point we started at, times the change in x. Okay? So if we're going by tenths, then our change in x every time would be 1/10, 1/10, 1/10, or whatever the case may be. Questions? Alright, showing your process here was worth 1. 1 for having the answer right, negative 5/4. So 2 altogether there. Alright, the next part here says we want to find the limit as x approaches 1 of f of x cubed minus 1. So, as soon as we see a limit on a BC problem, first thought should be what? It might be L'Hopital's rule possibly, especially if it's a fraction like this. It could be a 0 over 0 or infinity over infinity. And we can see pretty clearly that if we put a 1 in here, we're going to get 0 on the bottom. So we'd have 0 on the bottom. And we know that f at 1 is also 0. They told us that, even though we don't know what f is. Okay. We know that f of 1 is 0, so it is a L'Hopital's rule problem. So if that's the case, then we'll do the derivative of the top, derivative of the bottom, and get that. Okay. Alright, what do we know about f prime at 1? we know on the bottom that we're going to have 3 here because 1 and this will give us 3. Okay. But what about f prime at 1? Isn't this f prime right here? So if that's f prime, I can't put 1 in there though because 1 is not an x, 1 is an x value, not a y value. So what do we know though about y? When f is 1, y is, it's 1, 0, isn't it? Okay. So ultimately we get 1, 0, 1 minus 0 here, and we'd get 1. So answer would be just 1/3. 2 points here. 1 point for using L'Hopital's rule to get the expression for the limit that we can actually evaluate, and then 1 point for being able to plug in the numbers correctly and getting 1/3. Alright, questions? Alright, and the last part, we just have a separable differential equation to deal with here. So in part C, unfortunately this time it's only worth 5 points instead of 6, so they steal a point from us for standard 6 problems on this one. But bottom line here is if we do our 1/1 minus y dy dx on this side, separating the variables is worth a point. Anti-differentiating, we'd have, keep in mind you got a little bit of a chain rule issue here because your argument's negative y instead of positive y. And really, I mean, you can use substitution here if you want to, but ultimately it's just going to be negative natural log of absolute value of 1 minus y, and then x plus c over here. So if you chose to use u substitution, you'd wind up with just a negative du out in front, negative u du. Okay. Negative 1 over u du, I should say. And ultimately would yield this negative out in front. 1 point for finding the antiderivatives. And then from there, putting a c on there gives another point. And then from there, finding the initial condition here being 1, 0. If I were to put a 0 in here and a 1 in here, I would wind up with negative natural log of 1, which is ultimately 0. Gives me my negative 1 as my c. Another point for finding c. And then negative natural log 1 minus y equals x plus 1. And then from there, I would divide, minus 1. I would divide here and get negative natural log of 1 minus y absolute value negative x plus 1. And then if I compose both sides with e, I'm going to get 1 minus y e to the negative x plus 1. And I'll just add y and then subtract that, so it's going to be 1 minus e to the negative x plus 1 equals y. Since y is negative over here, I'll just add it to the left, add it to both sides, and then I'll subtract the e. Doesn't really matter whether it's on the left or right. As long as we got y by itself, we're good to go. And the final point was for solving for y. So if you solve for y correctly, you get the 5th point. And that's that. Any questions on any of the steps on the separable differential equation? Okay.